Hi guys. Sorry for the late start. I kept forgetting where I put this particular Zoom link. I don't think I ever made a new one after Monday. I don't know. Keeps disappearing on me. Anyway, you guys look just bright-eyed and bushy-tailed this morning, looking good. Franklin's got the lights on this morning. Grace has got some breakfast. Yummy. Okay. Oh, so fun. Good morning. Good morning. Okay. We're going to jump in and try to get a bunch done in chapter 36 so that we can continue to move forward. If somehow you've been up a bunch already and up on our haiku, you've noticed that some drop boxes have appeared. And I'll talk about this more in our bigger Zoom in a little bit, but you'll see that I added a drop box for the notes. And the due date is not really till like the middle of spring break. Not because I want you to be doing work on these notes any longer than you need to. Again, we're doing ecology and just pushing it aside, but just so that whatever, there's no pressure to finish them right now or ever, I don't know. I just made it for like a later date and just turn in something there. Like if you've been coming to these sessions, which most of you have, or at least been watching the videos and you're taking similar notes as what I'm doing, just turn those in at the end, get some points. Doesn't have to be beautiful. You don't have to have every single vocab term, just get something in eventually into that Dropbox. Great. Okay, here we go. Alrighty. Red? I don't know if I can write in red. Let's see, how about blue it is. Okie dokie. Uh-oh, I lost a page of notes. Oh, never mind, no I didn't, okay. Okay, so this is chapter 36 now. Again, we're jumping around. And we're talking about populations today. Can everyone hear me okay? Great, great, great. Okay, so a population is a group of the same species living in the same general area. And if you want to study populations, then you're going to become a population ecologist. So there's lots of different things that you can study about populations. One of them is the density, which is the number of animals in a given area. And again, those animals that we're counting as far as density are of the same species. An area is just some defined unit of space or volume. So like an acre or a square kilometer. I don't know anything about this term, but I'm going to assume it is a form of measurement. A league. And if we're looking at density of a population in a specific area, then one of the things that we can study within the density is the dispersion pattern of the species. And the dispersion pattern is basically how spaced out or clumped together the species are. I guess I shouldn't really say animals, I should say organisms. Because we could be talking about some phytoplankton or trees. So dispersion patterns come in 3 different densities. You've got clumped, uniform, or random. Clumped, or where all the resources are close together. Which drives food competition. But the good news is that when everything's clumped together, it decreases predation. Uniform, just like it sounds, is where the species is evenly distributed throughout the area. And that often leads to territorial behaviors. So maybe just give yourself a star to remember that a territory for a species is different than a population. You can still have a population of, I don't know, say lions, in a large area of a desert, or not a desert, a savanna, but within that population of lions, there could be 2 or 3 prides that are competing for resources. And lastly, random means that there is no pattern. And it's completely unpredictable. Who knows what's going to happen? And that's because the weather can often be changing, specifically, the wind, which can blow plants and seedlings in new directions each season, or within a season, changing things up. So of the three of these, clumped is actually the most common. Another thing we can study when we study populations is their survival rates. And that can be done twofold. One on a life table, which basically tracks numbers of species and their survival. Oops. I use this word that I really am not a fan of as far as statistical survival rates, and they call that survivorship. And then you can take the numbers that you create from a life table that tracks the survivorship and graph it on a curve. So just a little example of that. On our x-axis, we've got max lifespan. And on the y-axis, the percentage of survivors. Oops. And then you've got three different plots that can arise from a species population. You've got type 1. Let's make it a different color. Who seem to live a long time, but generally have less offspring. This can also be known as your K-selected species. And then we'll skip over to type 3, which is the opposite. And as you can imagine, they have many more offspring, but short lifespans. So if these are opposite of type 1 and therefore opposite of K-selected, what would they be?
R selected.
Great. And then right in the middle of these two, a nice happy medium is type 2. And they literally are just a nice little mixture. And the majority of the species actually fall into type 1 or type 3, and there's less than you would think that fall in the middle in type 2. And hence the development of K or R selected species. However, because there is an intermediate space and there's no real gray area for selected category, these tend to be a little vague. Can someone think of an example of a type 1 species or K-selected species?
An elephant.
Great. Oh, I drew his smile over his nose. That doesn't really make sense. Okay, and an example of an R-selected or type 3 species?
Fruit flies.
Great. Also really easy to draw, thank you. And then maybe something that's kind of in the middle.
Like mice or something?
Okay, mice would be a good one. Yeah, usually they do tend to have a fair share amount of offspring, maybe 4 to 6 rounds of offspring in their lifetime. Their life isn't too short. They can live a couple years. I like that. Mice are great in here. So we're many birds. Try to give you maybe another 15, 20 seconds on this page and I gotta switch to the next one. This is a random question, but is the other side of the Apple Pencil an eraser? I've always wondered that. I have this tablet from school that has like a pencil that came with it, this guy. And it's nice because I can do these annotations for you guys, but I keep flipping it over and trying to erase with the other end, and it doesn't do anything. It makes me sad. Alrighty. This is still chapter 36, but we kind of jumped around a little bit because we went like 36, 1, 2, 3, but then we skipped all the way to 8, and now we're back to like 4 or something. Oops, let's put that in green now. It's kind of hard to see. Purple. So we're going to look at the exponential growth model. So there's a lovely equation for this. It is G equals little r times big N, where G is our growth rate. N is the population size. Remember, a population is of one species. So it's not all the critters living at ESHS, it's just the number of patrices. And little r is the per capita, which is an individual's contribution. A per capita rate of increase. So if we have 4 Patrice squirrels on campus, and each of the 4 Patrice squirrels has a per capita rate of increase of, let's say, I don't know how many babies a squirrel has. Anybody? Should have picked an example of something I know about. Oh, has anyone seen a baby squirrel? I mean, that would be the cutest thing ever. Well, we'll just make it up. We'll say each Patrice has 4 mini Patrices. So per mating season, oh, somebody put something in the chat. Let's find out what it is. Oh, no worries, Myra. See you soon. Okay. And let's say they get 4. Lots of 4s. So their little r actually ends up being 16. So then when we plug it into the equation, we get G equals 16 times 4. Math, please. 48, 44, 49, 64. There we go. So that means that if we started with 4 squirrels in a population and nothing was going to hunt them down, the resources were strong, everything was good, their growth rate is 64. That means we'll have 64 squirrels by the end of their cycle. That makes sense. Of course, what's contingent upon things like mating happening? What do you have to have? Gotta have members of both sex in order for this to be possible. But in any natural population, that's going to happen. Unless all the female squirrels have an uprising and move away. Okay, so I wanted to quickly, hold on, let me find my notes for it first, but I wanted to quickly revisit our Simpsons diversity index from yesterday. Aha, I found it. because I had a nice little chatty chat with Miss McCann, and she helped me look at both of the equations you guys were given so that we could figure out, if they were actually the same or which one is easier to use. So I'm just going to revisit that really quick. If you want to go back to that place in your notes, you totally can, or just add on. Remember, this particular calculation is crucial to your Patrice Padlet this week. So that's going to show up this afternoon. Excuse me. And it's important that you are able to easily manipulate this calculation. I'm just going to write both of them down. So yesterday, the one that I gave you was 1 minus the total sum of n over n squared. Where little n was equal to the total number of types. No, we changed this. Why does it look weird on mine? The total number of species in a type. And big N is the total number of all individuals. But then Moira pointed out that in the Khan Academy, the formula is just slightly different. And that looked like D is equal to 1 minus the sum of n, that's me. The sum of n times n minus 1 over big N times big N minus 1. And when you look at it in the Khan Academy, you might notice that there's like these little i's next to the little n's. All that means is at the start, meaning like initial, meaning we're not taking into account necessarily like offspring that occur or loss of species in the meantime. So it's just like an initial count. It's just, what we see in the picture, for example. The statistical data given, not necessarily any change that's occurring. And after doing these with Ms. McCann, number one, we know that these equations are the same. So that's good. So it doesn't matter which one you use. And Ms. McCann assures me that all of you will totally know how to do both of these, even this one on the bottom, which stumped me a little bit. But when she explained it, it is actually much easier. So let's just take an example. If we have a population of circles, triangles, squares, and stars again, where the population of circles is 6, the population of triangles is 4, the population of squares is 2, and the population of stars is 1. First of all, let's just set up our variables. So we know that all of these numbers are our n values for each of the different species. And our big N is equal to what?
13.
13, great. Picked a terrible number again. Why do I pick terrible numbers? So when you go to set this up, you still have d equals 1 minus, but in showing me how to do this, it makes way more sense to set this one up because you can kind of do it really fast. Because when you're looking at this over here, that n times n minus 1, we can do those really, really fast in our head with these numbers. So if I'm doing the sum of these, it basically looks like 6 times 5 plus 4 times 3 plus 2 times 1 plus 1 times 0. And then divided by that big N times big N minus 1. So the good news about it is we keep nice big round whole numbers when we do it this way. And it's easier to type the whole thing into one calculator sitting rather than the way we were doing it with the first one where we were having to like get these decimal answers because of the squared and then kind of write those down in between and then do multiple steps. I can see Ms. McCann's point that this one is, you set it up, you have your problem, and now we can just type this in. So, and we could even do the top row in our head probably because we've got 30 plus 12 plus 2 plus 0. And so even Miss Mason-Net can do that in her head. And you guys will all check me to make sure that I'm right. But that looks like it's 44. And I might even be able to do 13 times 12 in my head because I know 12 times 12. So 156. So then that's an easy one to punch into my calculator. And I got 0.72. Which to me tells me this species is pretty diverse. We're getting definitely closer to the 1 side than the 0 side. Or not this species, this population. Not this population, this community. Oh boy, so many vocab terms. How do we feel about that? Cool. So long story short, I don't care which one you use when you look at the Padlet today or whenever you get to it. You can use either one of these, but just, be consistent and have a little fun. Okay, this is good timing and a good place to pause so that you guys have a little bit of a break to get maybe a snack or another cup of something for our next Zoom session if you're in second period. So if you're in second period, your Zoom starts at 9. If you're in third period, your Zoom starts at 10. And I know it's like kind of crazy today to do it in different periods. This was the request by administration to keep our Zooms to our own period times so that all teachers had equal opportunity to their students. Still doesn't seem like everyone's sticking to that. I know I didn't last week, and so we're all just still learning and being flexible. So if for some reason you have another Zoom with another teacher and you need to prioritize, totally cool. There's no sweat off my back. You know that I always record the Zooms and you can always view it later. You won't have the opportunity to meet up with your group and do the activity together, which is kind of a bummer, but you can still do it on your own and turn it in. No harm done. So do you, but hopefully I'll get to see you again in just a little bit. Anyone have any questions? All right, see you soon. Oh, I'm going to send out a blast right now, but check your email because the resources you need for the Zoom today will be in your email. Okay, see you later.